I've been so worried about trying to make sure I get the technology working. I've been forgetting things like announcements, and some of my lecture preparation has also slipped on that. So a couple announcements here. First of all, I don't know what the schedule is at Southwestern, but here at Union College, we don't have school on Monday for Labor Day. Hence, there is no class on Monday. So the next time I see you after today will be Tuesday when we have lab. Now, we have I forgot to make specific reference to this last week. We have a lab quiz that's due 5 minutes before the start of lab. So that means at 11:55, the lab quiz is due. And that lab quiz is on Moodle. Since I forgot to announce it last week, I went and excused everybody's score who didn't get a perfect score. So that way it can help the people's grades who got a perfect score, but it won't hurt anybody's grade who didn't get a perfect score in the one last week. Now, if we get to the end of the semester, there's one person that had 85%. If their actual lab percentage somehow manages to be below 85%, I'll go ahead and count it, if it helps the score. But I don't want to penalize people when I forgot to remind you for the first time around, lab quiz. So there'll be a lab quiz due at 1:55 p.m. on Tuesday, and then we'll have lab at 2. Question, Hannah?
When do those quizzes open?
The quizzes should have opened before school started this semester.
They're all open right now?
Yeah.
Oh.
Okay. Now the lab reports. There were a few people who had problems uploading the lab reports. The problems can be broken down into can't figure out how to merge files together, and the file's too big. Now, the file too big is, I think, a function of your scanner. Like a couple years ago, I had an art student who used a really good scanner with lots of detail and was creating huge files. And so, got to find a way to get it down. Our limit is 20 megabytes, I believe, for Moodle. I've tried to argue to make it higher, and they're worried, no, too much space will be taken if we make it higher. So what I did, there was a student who sent me, his was, I think, 96 megabytes. I first printed it with the PDF-fill PDF driver, and that lowered it down to like 26 megabytes. And then I printed it with the Microsoft PDF printer, and that lowered it to just a little under 10 megabytes. Just obviously it's throwing away information, but it didn't look different to the eye. It was throwing away detail that we can't really see. So that's the only, you can also find, if you do a search on the internet, you can find websites that will allow you to upload your PDF and then download a compressed version, one that doesn't have as much file size. Okay, the second thing is how to manipulate those files. So I'm just going to go through and show you how to manipulate those files using, that was not what I wanted to do actually, using a student's example that the student agreed to allow me to use. So I'm going to open up the PDFill tools. This underneath is the website where you download it. I downloaded the beta copy here just to get the latest of everything. And so over here you see a total of, I think that's 12 files that the student had to put together. Now the first thing is, if I open this file, open the file, what I notice is the scan copies, and I checked each one, the scan copies are all upside down. Whereas if I go to the graphs, the graphs are right side up. So what I did was I went to my PDF fill tools, and I first merged all of the handwritten ones she did. And you can't use the pen as a stylus, it turns out. So I'm just dragging them in there. And of course, if you were doing this on a normal computer, you could just go ahead and grab them as a group. Now you notice I got them out of order. So I'm just going to select the lab 2.4 and move it up. Or I could have, since they're all nicely named, there's actually a sort button, and it would have sorted it for me automatically, which is kind of cool. So now I'm going to save this, and I have to give it a name. So I'll just call this hand upside down or whatever that comes out as, because my handwriting's not always read correctly. So there are the files saved, but they're all upside down. So the next thing I need to do is to flip them. So I'm going to go to the rotate and crop the pages, and I'll select the one I just made that has them all upside down. Make sure if you're going to do all of them, you can only do one page or all pages or odd pages or even pages. So I'm doing all pages, rotate by 180 degrees to flip them, save as, and I'll just call this rotated. So now they're rotated in the correct direction. Now I need to add in the graphs. So I go back to merge PDF files, and I will first find my rotated there, put the rotated one, and then all of the graphs. One, two, three, four, yep. And save as, and I'll call this final. And now I have the PDF with all of them rotated the right way and put together as one file. As a final thing, let's say that I had put them out of order. If I put them out of order, I'll just go to split or reorder pages, and I'll take the final one and just change the order. So make it 1, 3, 5, 2, Now, if all the commas were read, which I don't think they were, this will be jumbled because I'm putting them in a random order. And so now I have it with them all out of order because I was messing around. Okay, so that's how that PDF fill or PD fill tools can really help you. It allows you to manipulate those files. And I appreciate the student allowing me to use her files for the demonstration. So if you have questions, go ahead and email me or contact me so I can help you, so we can avoid people having problems getting their labs done or turned in. Okay, remember we're session ID, web, PHYS, and clicker channel number 33 if you're here in the classroom. We're going to finish up talking about two-dimensional motion. And like I said, I've been so worried about the technology, I don't think that I prepared my lectures enough. So there's still going to be a little bit of stuff that I really should have made plain in previous lectures that I don't think I got through. So graphical vector addition. Graphical vector addition is done by adding the vectors, head to tail, tip to tail, however you want to call it. So this is showing adding vectors F1 right there and F2. And so the method is to first draw F1. At the end of F1, you put F2, and then your resultant, which is the fancy word for the answer, is the line that goes from the place you started to the place you ended. And if you are doing a graphical addition of vectors, you will need to make sure you measure the angles right and have a scale so that when you're done, you can measure the angle of the resultant and the length of the resultant. And from that resultant, using your scale might be, for instance, scale 1 centimeter equals 2.5 meters. So I'd measure this and I say, that's 2.2 centimeters, and hence, using my scale, that'd be 2.2 times 2.5 meters per centimeter, and that would give me, 55? I don't know. 5.5? Yeah, 5.5 meters. It's not like I thought this through before I made up random numbers. So that's how we do the graphical addition. Graphical addition is nice for seeing how things work, and sometimes it'll set up a problem really easily. I'm going to do a homework problem, one that's actually due tonight. I'm going to do a homework problem in just a moment, that you'll see looks really hard. The way the textbook, I think, wants you to do it is really hard. The one we did, Katie. But there's an actually really easy way to solve it by doing it graphically. Oftentimes, we like to do it what we call analytically, breaking them down into numbers and adding the numbers. So I'm going to do that after the homework problem I'm going to do. So vector addition using components. One last reminder about the trigonometric functions we're using, sine, cosine, and tangent. These definitions only work if it's a right triangle. So you see a right triangle drawn. And the definitions of opposite, the side opposite to theta is over here because it's not part of what makes up the angle theta. The hypotenuse is the side opposite to the 9-degree angle. And the adjacent side is the side that is not the hypotenuse that's making up my angle theta. So if I was using phi, that would, or phi, I pronounce it phi. It's like the only one that I actually pronounce right that other people pronounce wrong. Most of us say things like pi. In graduate school, I had a Greek classmate, and we're going through, and she says, like, you know, circumference is equal to 2pr. And I'm like, 2pr? Oh, yeah, I forgot you Americans pronounce it pi. Apparently, we pronounce these things wrong. Anyway, so I always say phi. Other people generally say phi. And a few people say photon. Okay, our first clicker question. This will take a minute. I forgot to start the clicker, so you got time to get ready. I was so worried about getting the camera set up and all of those things. Come on, clickers, start up. I actually started an hour early because I wanted to make sure I had everything done. Good times. Web Fizz. PowerPoint is coming up. We're almost there. Okay, now, whoops. Well, oddly enough, it doesn't look like it's. What was the question?
How much time do you give us to answer each question?
I usually give somewhere around 30 seconds. Okay, now you can answer. So if you'd answered before I said now, go for it again. Yes, ma'am.
One on smartphones.
Yes.
Yeah, correct answer is highlighted in green, and all the other ones are in red.
Oh, that's perfect. That you won't get it wrong now, will you? Okay. That I can actually fix that, but it would. Yeah, we'll just not worry about it today because it would make us have to answer this again. Okay, I'm going to stop it here in about 2 seconds. Okay, so our answers here are very clear. I will save Manawa having to answer because everybody but one person answered the same answer. They must be perpendicular to each other. Now, of course, the reason I generally have somebody answer is to explain the why of it. The simplest explanation of why they have to be perpendicular is because we want to be able to take our vector and break it up into two pieces where a change in one direction doesn't affect the other direction. If they're not parallel, like if you have things like this and like this, if I have an object and it moves from here to here, it has obviously changed in the direction parallel to my x as it changed in the y direction. we need them perpendicular so that if I move from here to here along one axis, the other one doesn't change at all. That is, they need to be independent. Okay. Now, analytical is the method I'm going to actually solve this problem. It's graphical and analytical together. So I want to talk about the methods for analytical solution of a vector addition problem. So the first step in the analytical solution is to make sure you select a convenient set. And I'm going to underline the word convenient because I'm going to take advantage of that right off the bat. Set of mutually perpendicular coordinate directions and add them to the figure. Then break each vector into its components. As you use sine and cosine to break it into how much in the x direction, how much in the y direction. Then you add the like components. You might remember me talking about my high school teacher with the, you can only add apples with apples and oranges with oranges. You can't make the fruit salad thing. So you add the x components together and separately add the y components. And mathematically, if you have two vectors, the x component of the first one plus the x component of the second has to equal the x component of the answer. The y component of the first plus the y component of the second has to equal the y component of the answer. So if you're doing two dimensions, you actually have two equations, one with the x components, one with the y components. Once you have found the components of the resultant, use the Pythagorean theorem and tangent to find the magnitude and the angle. So let's go to a picture from the textbook. I should ask, but I'm not going to, how many people have looked at this problem in the homework. You have a problem that basically has this. You have two vectors. They're VA and VB in the homework problem, and a resultant that's V total in the homework problem, and you're supposed to add them together. And so this slide from the textbook shows graphically that vector A was broken up into its x component and its y component. And vector B was broken up into its x component and its y component. And then you take the sum of the x's is equal to the x component of the resultant. The sum of the y's is equal to the y component of the resultant. And so you would need to, go through that step. Now let's look at the actual problem. Here's the homework problem. The numbers will be different for you than they are for me, generally speaking. But you have this, it's VA is 26.5, I can't read. VA has some unknown length at an angle of 22.5 degrees above the x-axis. VB has some unknown magnitude as well. And it tells us that the angle between VB and the resultant is 23 degrees. Between VA and the resultant is 26.5 degrees. And the resultant has a magnitude of 6.72 meters per second. And you're supposed to go ahead and find VA and VB. So I'm going to do that. Before I go to the next slide, there's one thing that I want to do. Work with some geometry. So we have here our variables. VA's magnitude, I don't know. VB's magnitude, I also don't know. V total, I know, is 6.72 meters per second. So as far as magnitudes, I only know one magnitude. As far as angles, I called it theta A because this angle here is the angle opposite to VA. VA is the vector right here. And so the angle opposite to is the one that doesn't participate in making an angle with. So that one's VA. And so we're given that VA is 23.0 degrees, or not VA, theta A. And theta B, theta B, this one down here, is 26.5 degrees. And then I wrote in a theta total. So this is going to be the first information from trigonometry for today. It doesn't tell us that angle, but I can find it using my trigonometry knowledge. Right? That's why you're well set if you understand trigonometry for this class. So what rule can allow me to find what that theta T is, theta total?
Sum of the angles is 180.
Okay. Aaron says the sum of the interior angles of a triangle is always 180 degrees. So that means theta total has to be the sum of the interior angles, 180 degrees, minus the other two interior angles. And so we can actually do that math. 180 degrees minus 23 degrees minus 26.5 degrees. Now, how many significant digits do I have in my answer? 3 is correct. Why is it 3? Okay, it's looking at the least significant digit for each number. And the least significant digits for each number, for the first one, the least significant digit is here in the units position. For the second and the third, the least significant digits are in the tenths position. The rule is the greatest of the least significant digits is the least significant digit of your answer, which I know, it always sounds mealy-mouthed to me when it comes out of my mouth. But that means I look at those and I say, well, units is bigger than tenths, and so my answer is only good to the units. Question, Colton.
Do we work in like columns in physics as opposed to sig figs with addition and subtraction, or
Well,
any sort of
I usually write them vertically so I can use the columns to determine the sig figs.
Okay.
But it's still using sig figs.
Okay.
Jordan.
Since 180 is not a value that we measured in there,
Mm-hmm.
would we not count that?
Yeah, actually, he has a point that I messed up on. 180 degrees is infinite digits, and I didn't even think about that. I wrote it down as 180 and went with that. So I was wrong. Jordan is right. It has 4 significant digits because this 180 is good to an infinite number of digits. That's a mistake on my part. I appreciate being corrected. I hate making mistakes, especially if it happens often, but being corrected is good. Okay, moving on then. We've got that angle is 130.5 degrees. The first step I said was to find a convenient coordinate system, and I underlined the word convenient. If you look at this, we have a coordinate system already defined, x and y. But I'm here to say that is not the convenient coordinate system, so I'm not going to use it. What would make it more convenient? I know Katie already knows the answer, but anyone else? Along the what? Along VA, okay. She said put the x-axis along VA. And yes, that makes it more convenient. Why? Because then VA only has an x component but not a y component. One less component in my vector makes it easier. So here I've rotated it so I have an x prime and a y prime. I don't just put x and y again because x and y were already defined. So I have these new prime coordinates. Jordan has a question.
Where did you get the angle of 22.5 degrees?
The 22.5 degrees was also given in the problem, but I just ignored it because it wasn't pertinent to what I needed to solve here. But yeah, it was given in the problem. So I wrote down there the theta total that we calculated from the previous slide. And now when I look at this and I break them into components, I see I'm going to need another angle, the one I marked as beta, which of course is also not how the Greek people say that letter. How can I find beta? Okay, I have a straight line with a line that crosses it. We form, supplementary angles? Supplementary angles add up to 180 degrees. So if one side is theta t, the other side has to be 180 degrees minus theta t. So I have to have beta equals 180 degrees minus theta t. By the way, Joel, I took out the battery, put it back in, and then the pin worked. It was the battery. But the battery's not dead, so apparently the hardware and the pin fouled up. Or it crashed, I don't know. Okay, so that's going to be 49.5 5 degrees is what beta is. Is that correct? Anyone want to correct my math? Okay. So now I need to break these up into components. So I am going to write VA vector equals, and then I'm going to put the x component first. So what's the magnitude of the VA vector? What did I have in the previous slide for the magnitude of the VA vector? I had a question mark. I don't know it. So I'm going to put VA. I don't know how big the magnitude is. Notice that doesn't have a vector sign. It's not a vector without the vector sign. So that's just the magnitude now. And VA is all in the x direction. So I'm just going to put the x hat. I'll put over here plus 0 y hat. Remember, the x hat means in the x direction. The y hat means in the y direction. And I better use the primes, otherwise I'm lying. So VA I broke up into components really easily. That's why it was more convenient to rotate. Now let's go to VB. Once again, I did not know the magnitude of vector B, velocity VB. So I'm going to put VB as the magnitude unknown. How do I find the x component of VB? I have that angle beta. How can I use that to find the x component? Okay. I have a student that says use the cosine of beta. Why cosine of beta? Because the x component and the y component, they go like that. And VBX is the side adjacent to the angle beta. And so I'm going to have VB times cosine of beta in the x direction plus VB. For the opposite side, sine is opposite over hypotenuse, so it's going to be sine beta y hat. So there I've broken VA and VB vectors into their components. I also need to do that for my answer. So V total, and we look here and we actually know the value for V total. I'm still going to put a symbol in now, but we actually know the magnitude is 6.72 meters per second. It's just quicker for me to write V total than 6.72 meters per second. And now I look at the angle between, do you have a question? No. The angle between V total and my x prime axis, oh goodness, I forgot to put primes again. And I see that's theta A. So cosine theta A x prime hat plus V total sine theta A. I did these apparently half asleep because I labeled them last night and I labeled these backward. Right, theta A is the side opposite vector VA. So I've labeled them backwards. So that's why I had to change those to B's. Hopefully you guys can process that without running backward. Now I said this gives me two true equations. One for the x components and one for the y components. If you were going to solve this, which side would you choose to do first? The x components or the y components? X prime and y prime. Y prime. Why y prime? Because it has a 0. It has only 2 terms instead of 3. It's going to be easier to solve. So I am going to solve the y prime direction first. So I'm going to have 0 plus VB sine beta plus V total sine theta B. Oops, no, equals. Got carried away. Well, that's super simple to solve for VB. VB is equal to V total times sine of theta B divided by sine of beta. So now let's put in numbers. So that was 6.72 meters per second. Sine of 26.5 degrees over sine 49.5 degrees. And would someone be so kind as to give me a number for that? Mahala.
The subscript of B that equals that equation, is that a B or a 0?
Um,
For the subscript.
okay, the subscript here is a B. Okay, so we have 3.94 meters per second. Now, I would keep at least one more digit for moving on. What's the next digit? 3? So, right, I don't have 4 significant digits, but I'm going to keep 4 for continuing the problem. Because now I have to turn to the x prime and add up the things in the x prime. So I'm going to have VA plus VB cosine beta equals V total cosine theta B. Obviously, this is not hard math. VA is equal to V total cosine theta B minus VB cosine beta. I'm actually not going to take the time to put the numbers in and do the calculation now because I want to illustrate the method of doing it. This is the harder way. It's a brute force way. The only way harder would be to do the way the book expected you to do it and not change your coordinate system. What's the easy way? Using the law of sines. The law of sines relates the angle with the side opposite to it. And so this is very simple. It works for any triangle, not just a right triangle. Sine of 9 degrees is 1, but you know, you don't do it with the right triangle. So in this case, all I have to do is say, well, we calculate what theta total is, and we know what V total is. So if I want VA, I can just say, VA over sine of theta A is equal to V total over sine of theta total. So VA is equal to V total times sine of theta A over sine of theta total. Put in the numbers, and you have 6.72 meters per second. Sine of, this time I got the A and B right, 23.0 degrees divided by sine of 49.5 degrees. And what does that give me for VA? It's what?
3.453.
I swear that's what we got from for the VB before. Oh, okay, good, good. Because I was starting to wonder if I really did something wrong. So doing for VB over sine theta B equals V total over sine theta total, giving me VB is equal to V total sine theta B over sine theta total, or 6.72 meters per second, sine of 26.5 degrees over sine of 49.5 degrees. And doing it this way, well, actually, I believe those are exactly the same angles that you had when we worked it out over here, 26.5, 49.5, and 6.72. So, of course, it's the same answer that we got before. You said it's 3.9, right? Those two numbers are only good to 3 significant digits, but you can see using the law of sines here turned out to be far, far easier than doing it with our brute force adding vectors. But they were both really examples of doing it analytically. I drew the picture, but I didn't have to measure the lines perfectly. I didn't have to measure the angles perfectly because I was using trigonometric functions and getting things into actual numbers on my calculator. What are the advantages of doing it this analytical way, doing it with numbers on your calculator? Okay, it's generally more accurate. None of us is perfect at drawing vectors. This here, we don't have to have so much perfection. We have to be more perfect at punching a number on our calculator. Still not a given, but a much higher probability. So that's why most of us prefer to do things analytically, but it's important to understand the process, and that's why we have the graphical method. Now, our next clicker question, which I'm sure it's going to tell you what the answers are, is why are analytical methods preferred to graphical methods for vector problems? Yeah, I need about 10 more seconds. All right. We had 56 people, which it's got to be a modern day record. And great. It was 6, 0, 0, and 50. Now, this is a question of preference. So, shifting here to Manoa, is that pronounced right? Manoa, by the way, is in the Southwestern class. You'll have to turn on sound for me to hear. There we go.
Yeah, that's correct.
Okay, so which one did you choose and why did you choose it?
I chose D, all the above.
Uh-huh.
No real reason. It was just a guess.
Just a guess.
Yeah.
Okay. Now, this was mostly an opinion question, and most of us feel that it's more precise because we don't have to measure carefully the angles and the distances, and that it's easier because you don't have to measure carefully, and that it's faster because it's frustratingly slow to sit there and measure your distances. So that's why we mostly go with that. But it's not a given. It is a matter of opinion. Okay. So that's ending my talk about how we add vectors. Just making sure we've got that clear. I know I only have 12 minutes left for trajectories. We're going to do the demonstration. So a trajectory is the path that an object takes as it flies through the air. So if I take this ball and I throw it to Rachel, as it goes from me to Rachel, yeah, I was worried about hitting the light, so I threw a little hard and went too high. Okay, as I throw it to the cupboard above Rachel, yeah, you thought I was going to, I thought I was getting ready to check it hard. Okay, as I throw it through the air, it goes up, it comes down. We call its path the trajectory. And the actual shape of that path is approximated as a parabola. It's truly an elliptical section, but the Earth is large enough when we throw balls a short enough distance that to all intents and purposes, it's a parabola. So if we were to treat the Earth as if it was flat, then it's a parabola. So just go ahead and keep the ball until the end of class. Don't. Don't throw it at me in the middle of class. So we're going to be looking at how these trajectories work and how we calculate them. So I'm going to start by shifting to a little demonstration applet and then doing the actual demonstration. So here is a little applet that helps us work with trajectories in simple, easy to visualize situations. So I have a motorcyclist who's going to jump. He's, Evel Knievel. I know you guys aren't my age, but when I was a kid, Evel Knievel jumped the Snake River Canyon. So our daredevil is going to try to jump, and of course he wants to land on his pillows. Wants to land over here on the pillows, so he doesn't break his back or whatever. Daredevils break all their bones. Evel Knievel, bragged about breaking every bone in his body or something like that. So right now it's just set with some default settings. Set the angle at 45 degrees and travel at 8 meters per second. So he shoots. Boom! He overshot. What must Evel do to shorten up his distance? Okay, change the angle. Student up front said change the angle. So I'm going to go back to Gabriel. How should he change the angle? Okay, Gabriel says let's make it larger. So let's make that angle a little larger. They're roughly 50 degrees. And still overshot. Let's try larger still. 57 degrees. Okay, he hit it. Yay! No broken bone today. Did everybody agree with Gabriel on that? What would happen if he slowed down? Or excuse me, if he changed the angle to a smaller angle? Okay. Woo! Hit it again. It turns out that if there's no air resistance, which is what we're assuming, and if you're landing at the same height that you take off from, 45 degrees gets you the greatest range. That is the greatest distance. If you go steeper, it's going to shorten it up. If you go flatter, it's going to shorten it up. So either answer for Gabriel would have been correct. Yeah, he was in a no-stress situation. But of course, there are other options. Get back to 45 degrees. What else could he have done to shorten it up at 45 degrees? Slow down the speed. So, 45.4 because I can't get it exactly back to 45. So let's slow the speed down.
You just hit reset.
No, reset resets him on the ramp. It doesn't reset numbers.
Oh.
So here I've slowed him down. Slowed him down clearly too much. Speed him up some. Yeah. That would probably still be jarring. Speed up a little more. There we go. Now, I am not going to do this. It's actually a really funny story. Have you guys ever seen the movie Road Trip? It has some really inappropriate material in there. But it also has a sweet scene where this character says, I'd say that bridge starts at about this angle, and if we go this, got to go this far, if we go this fast, we'll clear it. And one of his buddies says, are you sure? And he says, about physics, I'm always sure. And then, of course, we have, his name's not Stifler in that movie, Scott, whatever, William. Yeah, he spits over there, breaks off the other side, and better go 65. And they go back and they jump it. It lands. Woohoo! I told you it'd make it. All the tires fall off. Everybody starts laughing. My car. I said we'd make it. I didn't say this car would hold up. Okay, so it's a great clip, right? It's good physics. I wanted to do this, run back, do the calculation. Well, I showed it in class. I was using, this was like, 1998 or so. I had this laptop. I was playing on my laptop because we didn't have DVD players in our classrooms. And I didn't have the sound going right. So they couldn't hear him, say all the equations and about physics. I'm always right, always sure. And so I was like, okay, this was like 8 seconds from the beginning of the chapter. The beginning of the chapter just starts with, well, I give us about, so long until we get, and it's inappropriate content there. But it's kind of mild. And I was like, okay, I'm just going to go back to the beginning of the chapter. Yeah, I pressed the back chapter, and it went back one more chapter. Now, I know you guys don't know the chapters of this movie, but when you went back one more chapter, you were in a ladies' locker room with a bunch of naked ladies. So here on the screen, yeah. So I closed the computer instantly, and it was smart enough that it was like, oh, he just didn't want to see it on his monitor. He still wants to see it on the screen. So then I had to disconnect the cables. It was a bad time. As soon as class was over, I went to the academic dean to explain what happened. I wasn't trying to show that inappropriate content. Okay, so I'm not doing that. I'm also not using the scene from the movie Speed. One thing to think about for both of those, you've probably seen the movie Speed. Okay, when you drive over a freeway, you generally aren't going to catch air. And if that bus was going to be able to jump over the gap that wasn't completed, if they completed it, still would have jumped over the gap. And so you would have had cars going over the freeway catching air every time if it was legit that you could just, drive the bus 65 or whatever it is and be able to jump the gap in the freeway. And of course, if you look at the movie, you can see when it gets to the end, all of a sudden the front of the bus pops up and then it goes up because they have to put a ramp there, like what we just did. Okay, now there's a second part to this that goes with our demonstration. The archer. Now I have to tell you the story that goes with this. This is a physics made-up story. There is a certain kind of monkey that gets scared when you shoot at it. And when you shoot, it just falls because it's scared. It's kind of, like a possum that, just loses consciousness when it gets scared. And of course, it's supposed to be with guns, but they were trying to make this so it was less scary, and so they replaced the gun with the bow and arrow. And so the hunter, when he shoots these monkeys, has to account for the fact that the monkey is going to fall after he releases the arrow. And so where should the hunter aim if he wants to hit the monkey? Question, Jonathan, or answer?
Straight at the monkey, because the arrow and the monkey fall with the exact same acceleration, so he will hit it exactly as it falls.
Okay, actually, I think in this case he drops instead of the monkey falling, he drops a coconut because we don't want to injure the monkey or something, but we'll see. So I said it exactly that. What about the speed? Actually, we don't have an adjustment for speed. That tells you right away, speed doesn't matter. Play. Yes. We have to shoot it straight at it, and Jonathan gave us the reason. Now, the people over Southwest probably couldn't hear him. Southwestern. The coconut is going to fall with the same acceleration as the arrow. If there was no acceleration due to gravity, the arrow would have gone straight, and the coconut would have just hovered, and it would have hit. When you release the arrow and release the coconut, they both start falling with the same acceleration, so they deviate from that path the same amount, so it still hits. Now, this is a computer animation. Now we need to switch over to the camera, switch to call 3. I have here a target. I just photocopied it today. No marks on it. And I'm going to hang this target from the ceiling with a little magnetic mount that's going to drop it at the same time that I shoot my ball. I have these things up here hanging so I can get the camera set right. I also need to connect the wire or it will never, ever work. I'm glad I remember now rather than after class is over when I'm saying, now why didn't that work? It worked so well in practice. All right, so here we have the target. Here's my ball. Hopefully this bright yellow ball will show up on the video. I'm going to recheck my aim here just in case something moved. Make sure that's turned off. I load my gun, arm my system, and we are ready to check to see if it's actually going to, when it's aimed straight at it, hit that with the drop at the same time. Now, the way this is set up is, this is a photo gate. What it is just something that will detect if anything breaks between it. And so when that ball goes between it, goes over there, turns off the electromagnet, and that falls. So, everybody ready to watch with keen interest? The interest is really important to me. There we go. Nailed it, right? Because I am a good monkey hunter. And now we can check my target, and you can see how close I was to actually hitting the center. See? Not bad. Physics, yay, works. Okay, so next class period, I will go through working out problems like that.